Okay, so now we're recording, doing a few things with you guys, getting you guys set up. Some of you guys probably have this solved by now since I was passing out some papers, but remember our main focus today, I'll come back to this and make sure that you guys were able to figure this out, but our main focus today is going to be a Centripetal Force Lab. The page for it looks like this, and so have this printed out, ready to go if you're at home, and if you're in class, then I give that to you guys. Well, okay. I had some other things lined up. I wasn't sure how long this lab would take. I thought it would take most of the class. It's going to take just barely all of class, looks like, so bump those to another day. You guys remember that AP classroom is going to be our main focus tomorrow, so make sure that you finish the multiple choice by tonight. Some of you guys have finished this already. Okay. Then your chapter 7 college physics homework I'm going to pick up on Friday. You guys know this already anyway, and this is on focus, but these 6 problems, just a reminder. Okay. Then yesterday I was talking about registration. So if you should have gotten one of these in your third block. I went ahead and posted this to Google Classroom, so everybody has access to this. Right? Got a registration link for electives. Also, along with that is starting in March, starting March 1st, you guys are going to be going to either the auditorium for e-learners or sorry, auditorium lobby for e-learners or the auditorium itself for if you're in class for registration. Most of you guys are class of 2022, which is going to be March 1st, 2nd, and 4th. Right? And then you go by last name. So block 1, block 2, block 4. Okay. This is also posted to Google Classroom. You guys can see your schedule. I can't keep track of everybody, so you're going to have to take initiative and keep track of when your time is. Sit in your planner, know what's going on. Okay. I've got a handful of sophomores. So sophomores looks like March 4th, 5th, 8th, somewhere in there. Okay. This is by last name. So anyway, there's that schedule. You guys know when to go there. Got a question last class. Should you go to class first? Check in with your teacher. That's probably a good idea. So show up, say hi, so I don't mark your absent, and then go take care of that. Like always, I record these things, so if you miss like 10 minutes of class, you can see what you missed there, right? And then science elective, got to get you guys signed up for. So I did show you guys sort of a version of this yesterday. Here's the physical checklist. I'm going to pass this around class. So here's your name. Come out. Okay, thank you. And Zoe, let me get you a paper. Right, so you can find your name and then check one of these boxes, one of these cells. So here are your options. We got AP Bio, AP Physics 2, Environmental Science Research, Forensic Science, Marine Science, or if you have all your credits and you don't want more classes, or if you're a senior, I've got a handful of seniors, go ahead and check this very last column, just so I'll get that. Okay. Now, I asked guidance a few questions. They did tell me that AP Chemistry is not an option, so don't choose AP Chemistry. We don't have a teacher for that right now. Okay, right, you guys good there? All right, so like I said, pass this around class. Just make sure you check one of the boxes. Now, you guys online, e-learners, how are you guys going to do this? Well, I created a grade column and focus for this. So either write down the science elective you want, or type it, just whatever's easier, and upload that straight to focus for me. Right, so there's a column for it specifically for this. Just write down one of these classes. So I'll say your name, I'll say which class you want. This page is also uploaded to Classroom, so you have a nice checklist right there, so you can see exactly what your options are. Okay? And then I'll give you guys some points for doing that. Okay? Also, the grade and focus, that column has a description. It tells you exactly what to do. It basically says this. Okay? So you'll be able to navigate that. Okay? Any questions about registration or anything so far? All right. Okay, so let's get to this Martian question. Ooh, this is really relevant just right now, isn't it? Because we just landed a rover on Mars. So what if there's like a probe that's orbiting Mars, right? Something like that. Okay? And then, of course, in class, you guys just learned the last couple of days how to figure this out. What would be the orbital speed in, let's say, like low Mars orbit? Here's what we've got. We've got the universal gravity constant right here. We've got the mass of Mars, this number, which is parenthetical here, it's about 11% of the mass of Earth. Here's the radial size of Mars, right? And maybe I got this probe, and here's the mass of that probe. Who figured it out? Jared, how fast?
It's
About 3,500 meters per second? That sounds right. I think you're right. Okay. All right, so take you guys through how to solve this. In fact, I'll back up and show you guys how to derive the orbital velocity formula, which I showed you guys already, but it's a good review, right? Actually, it links directly to what we're doing today. So what I would say is that, guys, this here space probe that's orbiting Mars, what forces are acting on it? Only one, the gravity pull from the red planet, right? It's its own weight, right? It's like Martian weight, right? Okay, that's it. So now isn't that weight providing the force that's acting as a centripetal force? Because if you turn gravity off, like boom, when this thing like fly off tangent to its orbit, like fly off into space, okay? But that weight is the force that's allowing it to go into orbit. So I'm going to say that the centripetal force holding it in orbit is equal to its weight. Like that. Okay. Now, you guys have formulas for these. A formula I told you guys for a centripetal force, you guys remember, was mv squared over r. By the way, that's going to be our lab today. Is we're going to prove this, okay? Empirically. Okay. And weight, well, all along in class we've been using mg, but I give you guys a more universal way to think about it. Remember, it's universal gravity constant times the mass of Mars times the mass of the space probe divided by the square of the distance between the two. And we're treating the entire mass of Mars as if it's at its own center. So the distance between the probe and the planet from a universal point of view is the radius of the planet. You guys got that? Okay. Oh, guys, what cancels out? Yeah, one of the R's. And what else? Yeah, the mass of the probe. So now I didn't give you the mass of the probe. Is this number relevant? It is not. It cancels out. So it doesn't matter what the mass of this is. The end result is going to be the same regardless. Is that true? But you guys know it already. It's just a reminder. We're solving for this. What's the orbital speed? One algebra step, square root. So the orbital speed is the square root of gm on r. Okay. Now, you may have memorized this. This is a pretty handy one to memorize, isn't it? Okay. You may have started with that. Okay. Since I gave you guys the values, I did take you guys through an algebra base page the other day where you guys saw some pretty similar stuff to this. Really good practice to try this out in the calculator. Make sure you can navigate scientific notation and radicals and all that stuff. So we got 6.67 times 10 to the minus 11 meters squared per kilogram squared. We've got the mass of the red planet is 6.39 times 10 to the 23 kg. And the radial size, the radius of this orbit, now I'm putting in low Mars orbit, so it's going to be a little bit more than the radius of the planet, but in the big scheme of things, not a whole lot different. So we'll go ahead and use the radius of the planet. 6.39 times 10 to the 23 kilograms. Okay. Something like that. Now, notice how I grouped this all together and it's all underneath this radical. I have noticed that a handful of students have not extended their square root bar over all the numbers. Make sure you do that. See how it's extended over the whole thing? Yeah, Kevin.
For V, already put the mass twice instead of the radius.
Oh, thank you. Why did you do that? Yeah, 3 point. Yeah, sorry about that. Good call. Good catch. That's 3.39, isn't it? Or, no, I'm sorry.
No.
I'm so messed up. I'm sorry, guys.
One of those days, one of those days.
Yeah, pretty much. And I'm recording this too. Woohoo! For all time. You're like, ah. All right, so good catch. Let's try this again. So 6.67 times 10 to the minus 11 meters squared per kilogram squared. We got, okay, the mass of the planet is this number, 6.39 times 10 to the 23 kg. Okay. And the radial size is this number, 3.39 times 10 to the 6. Okay, so I think I'm all right now, right? Is that right?
Yeah.
Okay, yeah. Thanks for catching these. 1 second, all right. All right. Okay, so make sure that you can plug this properly into the calculator. Okay. So I'll go ahead and do a try run with you guys. Right, so one way to do is you could chunk this down into smaller parts, do like this part, and then calculate this part, and then put the parts together at the end. I'm going to put this in the calculator all in one go. So I'm going to do second square root. I'll bring up a square root. Okay. Now, let me do something that's incorrect, just to show you why. Let's say I plug in this number at 6.67, blah, 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 and then I close the parenthesis and then open. Okay? Now, as soon as I hit close, the calculator stops square rooting, and then it just closes the square root right there, which is obviously not what I want. I want everything to be square rooted. Isn't that true? Okay. So here's one way to get around that, is to, when you open up the square root, open up lots of parentheses, like more than you need. Okay? Like you can't have too many parentheses open because everything's being square rooted. Okay? But you can have too few. If like you only have like one parenthesis, as soon as you close it, stop square rooting, that'll run you in trouble. Okay? So here we go. We're going to go 6.67 times 10 to the negative 11. Close, whoops, negative 11. Close, open. Okay. And then the calculator knows that means multiply. Got 6.39 times 10 to the 23. Close, divide by, open. And then 3.39 times 10 to the 6. Group that together. Okay. Now, this model calculator will automatically close the rest of the parentheses for me. Remember, I opened up way too many to start with. Okay. I know Microsoft Excel forces you to close each one individually, like manually. Right, but right. Yeah, so we're getting what Jared said we should get, which is about 46 meters per second. Well, if I had 3 sig figs, maybe I could say like 3550 somewhere there. Right. There you go. That is the orbital speed, right? V orbital speed. Okay. And then, yeah, it's definitely get rid of that. Good so far? Yeah, Joshua?
This came back.
Okay. Yeah, thank you. Right. Who else needs this table? Anybody needs this table? Right. Okay, so, yeah, finish passing this around. You guys online know what to do. You're going to just, you can reference this online for a nice checklist. Pick the class that you like for your science elective, upload that to Focus. Okay, so, you know that. All right, well, let's get back to this Martian question. And so I do have a follow-up question here, which is escape speed. So let's say we've been orbiting for a while, and now we want to escape Mars and come back to Earth. So we're going to fire the engines. Right? How fast do you have to blast up to? What do you think, Kevin?
Orbit speed times the square root of 2.
Ooh, I like that method. And what were you going to say, Jared?
I was going to say 5,000.
Yeah, all right, so Kevin told us how to do it, and then Jared gave us a specific number. Okay. You guys remember how, this is good review too. Okay. You guys remember how escape speed, we derived this from conservation of energy. It looks very similar to orbital speed. The only difference is I slipped a 2 underneath the square root. You guys remember that? Okay. Escape speed, orbital speed looks pretty similar, just there's a 2 right here. So doesn't that mean that escape speed would be the square root of 2 times the orbital speed? Right, just as a general rule. Ooh, so now if you have one of these guys, you can very quickly get the other. They're only different by a factor of square root of 2. Okay? And if we found this before to be 3546 meters per second, if I multiply it by the square root of 2, see what escape speed would be. 3546 times the square root of 2. Okay? I'm getting, yep, exactly what Jared said, 5,000 and some meters per second. There you go. Okay. Or, of course, you could plug in all the numbers again and do it that way, but you get the same number. Okay. Now, here's a side note on this escape speed. I've mentioned this before, but we're saying again that technically you don't actually have to reach escape speed to escape the gravity of a planet, as long as the rocket engines are on. Like you could fire up to like 4,000 meters per second and very slowly go, right, get away from the planet. Right? As long as the rocket engines are always on. Right? What escape speed means is if you were to cut off the engines and just use inertia to get away from the planet, in that case, you have to be going at least as fast. Okay? But you guys remember that, right? All right. So that's all a good warm up here. Right. Guys ready to move on, or anybody got any questions? I don't see anything in the chat online. I think you guys are good. Everybody ready? Okay, so let's switch over and look at the lab today. What we're going to be doing is trying to prove that the centripetal force is equal to mv squared over r. Okay? Now, for today's lab, and you guys remember this is your lab page, so you have this at ready to go. We're about to start checking through this. Okay? Today's lab, I'm not going to have you guys do a write-up. I know you guys do at least one write-up usually every week. For a few reasons. One of the reasons I'm not having you guys do a write-up is that the mentality behind this lab is a little bit different from how AP usually asks you questions. When the AP asks you to design an experiment, what you guys have seen is that the assumption is that you know what all the equations are, and that you're solving for something. Like last week, some of you guys asked questions like, what's the coefficient of restitution of bouncy ball? Or what's the spring constant in the spring? Right? And then that's more of an AP style question for a lab thing. Right? The mentality behind what we're doing today is going to be like kind of what we did with the car and ramp lab. We're going to assume we're cavemen. We don't know, in this case, what centripetal force is, and we're going to set out to find what that is. Okay, we're going to find it out empirically. We're going to piece the formula together. Okay, you guys get that? Okay. So here's my actual question: is what is the relationship among these variables to maintain equilibrium? Okay. What's our variables going on? We've got oh, I should put V in here. Yeah. This is one of those states, isn't it? So then V group, that was always there the whole time. Yeah. Right, so what we're looking at. Let me show you guys the physical materials, bring those underneath the camera screen so you can see exactly what we're looking at. You guys see this cylinder that is representing this PVC pipe. Right? See, I got the string strung through it, got the string, right? And then I got a couple of Play-Doh canisters, right? And what's inside Play-Doh canisters, I can pop in little lab weights to change the mass of these guys. Right? Like that. Okay. Now, okay, so I can get it so that I can swing the string, and I'll have one of these canisters swinging around, and one of these canisters like acting as a weight, holding it in place. Is that? Okay. And see, I'm trying to maintain equilibrium. Okay. Well, there's going to be some relationship among these variables, right? So that maybe this one that's hanging doesn't rise or fall. So this guy could be in true static equilibrium. At least the one that's hanging would be. Right? Now the one that's swinging, is this guy in true static equilibrium? No, because static equilibrium would mean that either it's at rest or it's moving in a straight line, which it definitely is not. It's on a curved path. So you might argue like dynamic equilibrium, meaning that this radial size would not change. So to maintain this radial size, if I, for example, knew the weight of this guy pulling down and the mass of this guy swinging around, there would be some corresponding speed. Like there had to be like some particular speed to hold everything together so that this radial size stays the same. You guys get that concept? Okay. Okay. And then wouldn't this weight hanging down be providing the centripetal force to hold that into place? Okay. So this weight is going to represent the centripetal force, and we need to figure out how does that relate to this radial size, the mass of this guy swinging, and the speed that it's going at. Right, you guys get that? Okay. And then, of course, the weight of this guy, this force pulling down, is really mass times gravity. Okay. Okay. Guys good? Okay. So that's going to be our setup. Right. So let's take a look at this lab page and see how we're going to make a sense of it. Because we've got a bunch of variables we're juggling. Well, G is a constant, so maybe I don't really care so much about G. It's just going to be some constant for us. Right? But other than that, I've got 4 variables. The way we're going to approach this, and this is a really long lab, so I'm going to maybe give you guys more information than I should, is that we're going to relate everything to speed. We're going to treat speed as the dependent variable. Everything's going to feed into speed. Okay, there's going to be some equilibrium speed that's going to naturally set up if I change any of these other things. Okay, because any of these other things are easier to change. Right. So couldn't these 3 things be independent variables? It looks like I have possibly 3 independent variables, right? Could change out the canisters. I could change this radial size, fix some radial size, right? So, that means we're going to have how many different experiments? 3, right? Because we can only have 1 independent variable at a time, and then we'll have to keep the other 2 controlled. Is that true? Right. Right. So that's why, if you look at this page, I got a nice table here, a bunch of space for graphs, which we're going to save the graphs at the end of class. And if you flip the page over, I got 2 more tables. Because I got 1, 2, 3 different experiments. You guys got it? Okay. So let's take a look at this table, see if we can make sense of this. Right? And then if you're at home, I know it's real small print on screen, so hopefully you have this printed in front of you so you can read as we're going along. Right? So I've got the mass that's hanging, right? No, notice it does say in grams, so we're going to be using grams today. Right? Then right to right at that, it says weight hanging. Now weight is an actual force, isn't it? Right? That's going to eventually provide the centripetal force to hold everything together. Right? And notice it says millinewtons, and it should make sense that normally we go from kilograms to newtons, right? Because kilograms like baked into newtons, right? So grams would be 1,000th of a kilogram. So doesn't it make sense if we multiply by 10 meters per second squared, we're going to get to like millinewtons, because milli is also 1/1000th. Okay, so that's where that's coming from. We got the mass swinging. I could change that out. 1 over mass, that doesn't make sense now. It'll make sense later on, so just hold on to that idea. I got the radial size, got radius. Okay, so meters, we can measure meters. Right? 1 over the radius, that'll make sense by the end of today. Okay. Now, you guys see how some of these are bold and some of these are not? I've got 3 values that are bold. Oh, those are the 3. Why are those bold? Yeah, those could be independent variables, couldn't they? Of course, we're going to just treat one at a time. So we're going to treat 2 of these as controlled and then 1 is independent variable. Okay? And then we're going to relate that all to speed. You guys see how the second to last column says v, like speed? Okay? But how the heck are we going to get speed from this thing? If I don't have a radar gun, if I don't have a motion detector, right? Can you guys use your creative powers to figure out how we're going to calculate maybe the speed of this thing? You can think of a way to do that. What do you think, Logan? Yeah, distance over time. So, like, do you think you guys can figure out maybe, 1 trip around could that be the circumference of the circle, right? And if you know the r, the radial value, you guys know circumference is 2 pi r, right? And then if you divide that by the time it takes to get around, that would be the speed, wouldn't it? Right? Call that instantaneous velocity or tangential velocity. But I'm going to try to use the word speed today, right? So v represents speed, right? Right. So that's what these columns leading up to the speed are for. I've got time sub 10 and time sub 1. So 2 different time columns. Right? You guys probably know where I'm going with this, right? So time 10 would represent, you guys know that would be like to swing around 10 times. And then we're going to divide that by 10 to get around once. Right? Why are we doing that though? Do you guys remember? Why let it swing around 10 times and then divide by 10? Why not just swing around once? Yeah, to account for random error, Jared is saying, right? Yeah, I was going to ask guys too. You guys remember there's systematic error versus random error? And I was going to ask guys which one it was, but you guys are way ahead of me. It's like, oh, it's random error, right? Systematic error is like if you always start the stopwatch late, for example. Well, can't really do much about that. But random error is sometimes you start early, sometimes you start late. Yeah, if you have to go around 10 times and then divide by 10, that could divide out what that error is. Something like that. Well, actually, you know what? That's actually what multiple trials are for too. Actually, this would be able to handle a little bit of each kind of error. Now I'm thinking of it too, because if you're a little bit late, regardless of what type it was, then that would anyway. The error is also divided by 10. Okay. So once we get that, here's how to calculate the speed. Right? 2 pi r is the distance, circumference, right? Divided by the time to go around once. Right? And we got that. Right? And then last column says to square that. That'll make sense by the end of today. Right? Right. You guys okay with that setup? Okay. Okay. All right. So let's go through and figure out which experiment we want to do first. Okay. So obviously the speed is going to be the dependent variable. That's going to be true throughout the lab. Okay. Let's start with changing out the radius. That's the easiest one to do just because I can leave the canisters alone. So let's have the radius be the independent variable. If that's true, then I'm controlling both of these guys, right? C for control, independent variable, dependent variable. You guys got that? Right. All right. So I need to figure out what is the mass and the therefore weight of the one hanging, what's the mass of the one swinging. How's this going to fit together? So turn my camera here. All right. What have we got here? We've got the items that I showed you guys. We've got a PVC pipe and a couple of canisters. We've got here. Okay. I've got a scale, like a triple balance beam, right, so I can measure mass. Right? Okay, so figure it out. Yep, pretty well zeroed out. Okay. I've got rulers here, but what's probably going to be more helpful today is it's actually a meter stick. So that's some measuring tools. All right, so it's going to go pretty good. So I need some kind of starting value. Now, let's say I have the purple one hanging and the green one swinging around. Okay. Of course, normally what I like to do is throw all these materials so you guys get your hands on these things, feel them out. Okay. So there's like some practical lab considerations. Which one do you want to be heavier? The one that's swinging or the one that's hanging? Definitely the one that's hanging, right? Because if they were the same mass, then you wouldn't be able to make this work. The swing one's just gonna take off and no equilibrium. Yeah, definitely the one that's hanging has to be heavier. Okay. And so let's pull this apart. Actually, what I'm gonna do is replace the string because after so many trials, it gets kind of warm. Okay. I do that, and I do get rid of that guy. All right, so string out. Get a brand new string on this guy. Oh, all right, so it has been cut for me. It's too long. Right. So keep this stick here. Right. Okay, the purple one I'm going to have hanging. You're right that I do want this guy to be pretty weighty. So right now it's a little bit overstuffed. So I'll pull some of these guys out. It's from last class. Got some weights in it. Okay. Let's see, what is the mass of this purple one that's going to be hanging? Okay. Throw this on here. All right. Oh, it's quite heavy. Oh, pretty close. Oh, that's it. It is 87 grams. 87 grams. Go ahead and tie string to it. We're making quite a few simplifying assumptions with this lab. You guys can probably imagine what some of those would be. Okay. Do you think we're assuming that the string is approximately massless compared to the canisters? Yeah. Okay. Do you think we're assuming that maybe like air drag and frictional forces are not going to be considered? Okay. Do you think we're assuming that when this swinging canister is, this green one is swinging around in a circle, that we're assuming that it's a basically horizontal circle, and that maybe not really like a 3D cone? It's be pretty close to that, right? Pretty close to a horizontal circle. And then, now the green canister, let's go ahead and use just an empty canister because that'll work pretty good. Okay, so let's see. Yep, zeroed out. Okay, empty canister. 6 grams. It's 6 grams. 6 grams on the empty canister, or well, the mass that's swinging. Okay, so 6 grams on the swinging mass. All right. Turn them on. Okay. Okay. And then here's the setup. It's just gonna go like this. Okay. So, okay. Now we go on some numbers on this page so far. So the swinging mass was 6 grams, which means that its weight would be 60 millinewtons. Isn't that true? And the man, yay, all right. Sorry, that was the swinging one. Okay, so what was the mass of the hanging one again? 87. Okay, so it's 80. Say 87. We should make this 870. 87. Okay. There you guys. What's going on? We're looking at. Okay. You know what? Scrap that paper. Messed up immediately. Okay, so you guys said the hanging one was 87 grams, which would make its weight 870 millinewtons, right? And the swinging one was 6, right? 6.0 grams. Right. Okay, this is what we got so far. Let's choose a fixed radius value, radial value. Remember, this is going to be, this is one we're going to change. Right. So this is going to be independent variable. I'm just going to go ahead and leave these canisters the same all the way down. So this is control, okay. And then this is eventually going to be dependent variable. Let's go, see, meters, right? We'll go 30 centimeters, so that'd be 0.30 meters. Right? Then we'll up it by 10 centimeters at a time. So 0.40, 0.50, 0.60, 0.70, 0.80, and 0.90. Okay? Those values all work out first. Okay? Okay. Now, since these other guys are being controlled, that means they're going to be the same all the way down. So let's just do some hash marks to say the same all the way down for these guys. Because those are controlled. So I'm not going to touch the canisters. I will be changing the radial value. Okay. Oh, I do need someone to have a stopwatch. So who has their cell phone up and ready to go and has a stopwatch function on it? All right, Joshua, you got it? Okay. Okay. So how many do this? I'm going to swing it around 10 times. Okay. I'll count from 0 to 10. And as soon as I say 10, then you stop it and tell me how much time that'll be, right? Okay, ready to go? Okay. Here. Okay. Let's go on. Okay. So we're starting in a pretty small radial size. Let's go 30 centimeters. That's about 30 right there, right? All right, ready? Okay. And 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Did you get that? 0.72.
No, 2 point.
Or, sorry, this one's better. 2.72. So that'd be 2.72 seconds to go around 10 times. Oh, so how long would it take to go around once? Yeah, 0.272. We're going to do that. 0.272. Right? Now, here's where ideally what you would do is we would do several trials of that, maybe like at least 3 trials and take an average to help get rid of random error again. Right? We're not going to do that today because this lab is so long. We're going to just save a little time. It does work out anyway. This is going to work out in the end. Okay? But you guys know that that's worth a point on the AP exam, just mentioning like do several trials, right? Okay, so ideally we should do that. Okay, so working our way down, let's bump this radial value up to 40 centimeters. Okay, so Joshua, are you ready? All right, get this going. All right, and 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 2.82.
Yep.
So 2.82. Okay. Let's bump this up to 50 centimeters. All right, and 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
3.65.
3.65?
Yep. 1 whole year.
Oh, yeah. Let's take it up to 60 centimeters. All right, ready?
Yep.
And 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
4 even.
Ooh, 4 even. 4.00. 0.4. All right, up to 70 centimeters. I'll turn the camera in a few minutes so you guys online can see the data table. But, all right, ready? And 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
3.95.
3.95?
Yep.
All right, 3.95. So 2 more. Let's go 80 centimeters. All right, ready? And 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
4.41.
4.41. 0.441. Right. And then finally, let's take this all the way out to 90 centimeters. All right, ready, and 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
5.15.
5.15. All right. Turn the camera for you guys online. We're doing, okay, so 5.15, 0.515. Right. Go down and hit all these velocity or I should say these speeds. Okay. So right, it says what to do, right? 2 pi r divided by t, and we reasoned through that earlier. So go 2 pi times this radius, 0.30, divided by t1, which is 0.272 for 1 cycle, 6.93 meters per second. Then at 40 centimeters, it was 282. That would have been 8.91 meters per second. And 50, we're up to 365, up to 8.61. We're doing, see, 60 was 4 even, at 9.42. The 70, it was 395, 11.13. 80, it was 441, 11.40. And then at 90 centimeters, it was 515. That's 10.98. All right, there we go. Okay. All right. There's other columns. If you fill them in or leave them blank, it's right. It's okay if they're blank. I'm not going to count. But you'll see why they're in the class. I'm actually going to have the Excel handle those for us, and we'll have just enough class time to handle those. Okay. You guys good so far? Okay, so now we've got one of the relationships down. We can somehow relate the radial size to how fast it was going. Looks something to do with like as the radial size gets bigger and bigger. Overall, it was going faster and faster. Right? You guys got with the 2 canisters controlled. Okay. But we're eventually going to turn that into one of these graphs. It's going to be, you guys see this one says V versus radius. Right? Basically, if I took these 2 columns right here and I plot them here, V versus radius. Right? Okay, so it's something to do with up and to the right, but is it a direct relationship? Is it curved one way or another? Okay. We will plug this into Excel later on and find out. Okay. But for now, let's grab all the experimental data. All right, so all we have to do is change what we're controlling and what we're treating as independent variable. Now, velocity, or I should say speed, is still going to be the dependent variable, dv, dependent variable. Okay. This time I'm going to control for the radial size. The last class, I used 40 centimeters. That worked out pretty good. Let's try 50 centimeters. Let's do 0.50. Okay. And that's going to be the same all the way down. 50 centimeters, so 0.50 meters. Okay. Because that's going to be controlled now, right? Okay. Let's do, and that'll be true for this last experiment also. What's dependent variable for speed. We're also going to control for the radial size, so let's keep that at 50 centimeters, so 0.50 all the way down. Okay. All right, then, okay, the canisters. For this one we're about to do, let's treat the swinging mass as the independent, and we'll control for the weight hanging, and then later on, we'll reverse that. Okay, and then that'll be our plan of action. Okay, good. All right. Now these take a little longer because I got to keep popping open the canisters and swapping out the weight sort of thing. But looks like the experiment we're about to do, I'm going to leave the weight hanging the same all the way down. Now let's take ahead a few steps. You guys did tell me a few minutes ago that for practical lab purposes, you do want the weight hanging to be more than the mass that's swinging, right? Right. So since I'm going to be changing out the swinging mass and be adding mass to it, right, as we go along, I probably want to make the hanging one pretty heavy. Wouldn't that be true? Okay. So that's what I'm about to do right now. So switch the camera over. Make this purple one, I'm going to have hanging. So do I like the weight of this thing? Look, how much was it? It was, yeah, was it 90 something grams almost? Oh, 80 something? 87? Yep, you're right, it was 87. Right. You know what, is that going to work for us? I think 7. Actually, I think we'll go ahead and leave that at 87. Let's do that. Right, so the hanging mass would be 87 grams. That'll be all the way down. Right? Therefore, the hanging weight would be 870 millinewtons, wouldn't it? Assuming that gravity is 10 meters per second squared, that's going to be our assumption, right? So, if you guys online, here's what I just did. Right? Is that the mass hanging is 87 grams, therefore the weight hanging is 870 millinewtons. Okay. That'll be controlled all the way down. Okay. All right, so I gotta change out this green canister though. Now right now it's empty. I'll go ahead and do the first one is just an empty canister, and it should be 6 grams. But let me just double check that with the measurement. Yep, it's still 6 grams. So for the first trial, it'll be 6 grams, pretty similar to what we just did. But we'll go ahead and rerun this experiment. So I guess technically we should have the data for this already, but let's do a second run. Hopefully we get something pretty similar to what we got before. Right, so I need to open this up to 50 centimeters. Right, Joshua, are you ready with the stopwatch?
Yep.
Right, ready. And 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
3.5.
3.5? Right, so you got, so this thing was 6 grams, that was 3.5 seconds, 0.35. Okay. I wonder what we got before for that exact.
3.65.
Oh, yeah, 3.65. All right, that's pretty close. Great, nice. Great. So that's what we're looking at online. Right. So if you guys are online, I'll probably go ahead and just try to see this data table for a while. I'm gonna try to grab all these numbers and then rotate the camera over to space and grab that. Right. So let's bump this green canister up a few grams. Right. See, we can go up to, see if I got some, okay, so I got 10, let me throw a 10 in here. Okay. So it should be up to 16, but let me just verify that. Yep, 16 grams for the swinging mass, 16. You guys ready to go with 16 grams? Okay, got the stopwatch? Okay, ready? And 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 5.39? Okay. So 16 grams. Got 5.39. 0.25. Oh, yeah. Not there. Good. All right. Let's see next. Okay, so need to bump up the mass scale. Let's throw in another. Got another tenor. Yep, it's 26 grams, as it should have been. So 26. Numbers add up. Good thing. Okay, so we're looking at 26 grams. Right, ready? And I should have had you guys predict whether it swings faster or slower, but you guys would have said what? Slower. You can see that too, right? And I can feel it. But, in fact, it's kind of hard to balance this thing already. Yikes. All right. All right. And 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
6.67.
6.67. 26. 6.67. 0.667. Okay. I'll probably even be able to get to the end of this table at this rate. Maybe not. Am I out of tens? No, I got one more. Yeah, let's have 5. Okay, so I'm just gonna add 5 grams to it. I hope this is 31. Let's find out though. Yep, it's 31 grams. 31 grams. Okay. Okay. So 31 grams. Here we go. Okay. And 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
7.87.
787.
Hang on.
787. All right. Okay. Toss another 5 grams in here. Yep, we're up to 36 grams. We're up to 36 grams right now. Ooh, this is gonna work. All right, and 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
8.57.
8.57. 8.57. 8.57. Okay. And I'm kind of getting at a limit here now. Let's see if we can fit one more row in here. Well, let me throw a 10 gram guy in. I don't know if this is going to work, but we will find out. Okay. Yep, we're up to 46 grams. 46 grams. Okay, you guys ready to go? 46? Yeah. If it doesn't, then we'll see. We'll see if this even works. Ooh. Okay. Yeah, I think it's barely going to. Okay, here we go. And 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
9.55.
9.55. Okay. We'll go ahead and have that as our last row on that table. So 46 goes 9.55, 0.955. Okay. Okay. So guys, double check my speed calculations. I'll do 2 pi r divided by time 1. So 2 pi r, now radius is controlled, so that's 0.5 meters, divided by t1. So this is 0.35. Okay. Did you guys say 8.98? Okay, so 8.98 meters per second. Okay. Right, then all I have to do is pop in the new time values all the way down. 539. Okay. I'm looking at 5.83. Let's see, 667 came out to 4.71. Let's see, 787 was 3.99. Ooh, look at that. It is getting slower and slower, just like you guys said it should be. Doing 857 is 3.67. And let's see, 955 is 3.29. Okay. Questions so far? Okay, all right. Oh, now we're moving on to the last experiment. Right, the last experiment. Uh, so I need to keep the swinging mass controlled. Also the radius, of course. Okay. What do I want to use? Let's go ahead and use. Let's think about this. Let's go 16 grams all the way down. I'll measure it out so that it comes out to 16 grams. I think it's a pretty good value. Okay. The smaller, the easier. So okay. We'll have that controlled all the way down. Okay. But I need to change out the purple canister that's hanging. Right? So I'm gonna do that. So switch this. All right, got. Oh, okay, so the green canister I need to change to 16. This should give me 16 grams. Let's just make sure it does. Is that pre-recorded value? Yep, it's 16. Okay, so we can keep that 16 number. All right, so that's all good. Guess I should have measured before I wrote it down. So it's more scientific. This purple canister right now. This guy's turn too. Okay. Now this guy better be. Let's see if I can get it. Should be about 26. Let's see if it is. Yeah. More than that? Interesting. This one's reading like actually like closer to 27. Huh. Oh, because it's got some tape and stuff on it too. Okay, so we're looking at 27 grams for the hang one. I'm not sure this is going to work, but it might. It might be that the hang one's too light, but we're going to find out. Okay. Does this even work? All right. Take the radius up to 50 centimeters, just like we've been doing. Ooh, yeah, it just barely works. I have to swing it around real slow. Right? All right, you guys ready? And 0, 1, 2, 3, 4, 5, 6. I messed up. Let's start over. Sometimes that'll happen. Okay. Take 2. Okay. And 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
7.11.
Woohoo! So 10.11. So 0 point, or sorry, that'd be 1 point. Whoa. 1.011. Okay. And so that was for, was that 27 grams, right? 270 millinewtons. So, you guys online, I know you can't see the data table right now. I'll turn the camera on when I do the calculations, so you guys see that. All right. Okay, let's give this purple one some more weight, which will make this easier to handle. Now, because when I throw more little lab weights in this purple canister, am I going to swing faster or slower? Yeah, faster. Should make sense, right? Let's throw in 20 more. Right? So you could add 20, but let's just double check, confirm that. Yeah, we're up to 47 grams right now. 47 grams for the hanging weight. 47 grams. Okay. So it's still kind of light actually, but a little easier. Okay. Is that great, Joshua? Okay. And 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
7.19.
7.19. Okay, so that was 7.19. Okay. I'll raise it another 20. It is now at 67 grams. 67 grams. All right, ready? And 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
5.62.
5.62. That was at 67 grams, 60 to 70 millinewtons. 562. All right. Let's pop in. Ooh, another 20. Yep, we're up to 87 grams. 87 grams. Ready? And 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
5.33.
Got 5.33. This thing's getting pretty full now. Space for another 20. Now it's at 107. Right, this way. Yeah, 107. Yeah, swing a little faster now. And 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
4.86.
So 4.86. Yeah. Okay. There. Huh. I think I'm doing this a little faster than my last class somehow. We've got kind of a late start here too. You're doing all right. How many more? Oh, yeah, I got another 20. Ooh, I think it's all I can fit in here anyway. So I think this will have to be the last trial, just because it's quite overstuffed. And that comes out to 127 grams. We're sitting on 127. 127 grams. All right, ready? And 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
4.23.
4.23. All right. Okay, so that was 4.23. And that was at 127 grams, so 1270 millinewtons. All right. Go grab all these speed values. So 2 pi r divided by t. So the 2 pi times the radius of 0.5 meters divided by, okay, so time on is 1.011 for the first one. Okay. So I'm looking at 3.11 meters per second. Okay. You guys are checking my math too, right? 0.719. 4.37. There's 562. 5.59 meters per second. 33. 5.89 meters per second. 486. Looking at 6.46 meters per second. And finally, 7.43 meters per second. Ooh, look at that. Speed's going up. All the way down. Oh, what's this in the chat? In the chat. It says, oh, okay, hold on, I got a tense question. Wait, I was thinking I'd fix that. Let me just double check my attempts real fast. Let's see. 1, 2. Okay. This one here. I still have. Where we have. Yeah, Danny, I've got you present here. I did mark you absent for like 2 seconds, and then you popped in right after. Yeah, so you're present. Yeah, but thanks for letting me know. All right. So, any questions about the lab up to this point? All good? All right, so let's figure out what we're going to do with this data. So we've got all this raw data in these tables. And remember where this is heading. Maybe I should have pointed this out before we got rolling on this whole thing, because I did tell you guys the setup. I told you the setup. We're trying to figure out the relationship among these variables. We're not really interested in G. We're just, that's a constant in the background. But these other 4 guys, we want to know, right? And you see these last couple of boxes here? It says, how are these 4 variables related? Okay. What we're going to do is, and you'll see why as we go throughout these graphs, we're going to relate everything to speed squared. Now, that might not make total sense right now, but it'll make sense when we're going through these. Okay. And then, okay, and then it says therefore solve for F. So now, in this lab experiment, what number is representing the force again? The hanging weight, right? The one that's hanging is providing, okay, this guy right here is providing the force to keep this guy in orbit. Okay? How does that relate to the other variables? Now, you guys know what the solution to this is going to be, right? Because you just applied it to solve for the orbitals to get Mars. It's like mv squared over r. Okay? But let's see if we can get to that empirically going through all these graphs. Okay, so, so first one says V versus weight hanging. Oh, isn't that the lab that we just did? Okay, so label your axes like this. Go V versus, well, weight hanging, we're going to call it F for force because the weight hanging is a force, right? Yeah. That is the force we care about. It's providing the centripetal force. Okay, so let me flip over to my computer. I'm going to present screen to share. Okay. Well, you guys are seeing my first plot numbers. I'm going to save this because they actually had some really pretty looking graphs, but yeah, maybe these are going to turn out really pretty too. We will find out. Okay. This is one of those labs that if you're pretty good with keeping the radius constant and on the stopwatch, then it's going to open. Okay. So here we go. Okay. Then turned to work out pretty good. Okay. And then otherwise though, these graphs can be pretty ugly, but we're going to find out how good we were. So let me go ahead and pop in these values right here. Then just take this data. So this first graph does refer to the one we just did. Right? So we did this experiment third. And the force values, the hanging weights, went 270 millinewtons, 470 millinewtons, 670 millinewtons, 870 millinewtons, 1070, and 1270. Okay, look at those. Okay. And then the corresponding speed values went 3.11 meters per second, 4.37, 5.59, 5.89, 6.46, and 7.43. Those would all be in meters per second. Oh, that's exactly what that graph should look like. Okay, so that's that. Now that graph that I just had you guys label the axes on, the top left graph on the front side, I guess that little tiny graph. Okay. Go ahead and scale. We're just copying that graph right there, right? So scale your horizontal axis, you guys see the horizontal axis is the force up to, well, it goes over 1,000, right? So let's see, 2, 4, 6, 8, 10. It looks like if each marks like 200 millinewtons. So this is in millinewtons, right? So 200, 400, 600, 800, 1,000, 1,200, something like that. Right. And then the speeds, well, the biggest speed was just, well, it was like oops, sorry, that's right. What was the biggest speed? It's like 7 point something. So, oh, so if each tick mark represents like 1 meter per second, because these would be in meters per second, to go 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay? That would be able to contain all your data. Okay? Let me flip the screen for you guys in class, or let's say for future video. See, it's gonna. Oh, oops. Let me see what you guys are going on here. Right. So see what I did. We're doing speed versus force, which is represented by hang weight. Okay. So I've got my axes scaled or labeled. Okay. Guys, it's it. Okay. So how it's scaled, about like that, labeled. Right. See, I've got my units labeled too. Velocities in meters per second, forces in millinewtons. Yeah, Morgan? Oh, yeah. Yeah. Thought there was one on your desk. Where did, oh, we go. Okay. Okay, so now that you've got that, put those dots about where they go. When we flip back over, we present, screen, to share, right? And we're all going to copy that graph that's on the screen right now on that little graph that you guys got in front of you. So, see, take this where I can see it better too. Now, right about there. 4, right about there. All right. Now, what basic shape does it look like would best fit through those points? Huh. Did you guys think it might be a straight line? Here's the thing. If it, what do you think, Kevin?
It kind of looks like a cubic root.
Ooh.
Cubic function.
Yeah, so Kevin's saying something about a root. Right? I actually like that better than a straight line, because if this were a straight line, wouldn't this have like a massive y-intercept? Right? And how would you interpret that? That would mean that at zero hanging force, there'd be some definite speed that it would be going at. That doesn't really make any sense though, does it? Right? For zero hanging force, it'd be like some speeds about 2 meters per second. That wouldn't really make any sense. I bet it's like a curvy looking function. Maybe possibly a square root, maybe a cube root, maybe a fourth root, some kind of root function, doesn't it? Right? Let me remind you guys some basic graph shapes that you guys see over and over in this class. Stop sharing my screen for a moment for the video. Right? So I've shown you guys these basic graph shapes in the past. I'm just going to try to whip them up real fast here. These aren't all the graph shapes, obviously, but these are some common ones that you'll see in labs in this class, and also that you might see on AP. Right? You guys remember there was like no relationship between two variables? These could all be like y versus x. I'm just making really general graphs, right? No relationship could be one variable changes and the other does not. Right? So now the points might be something like this, for example, right? Something like this. But basically, one variable doesn't care what the other variable is doing. Like in this case, in the first one, whatever y is doing, or sorry, whatever x is doing, y doesn't care. Y's like, I'm just going to hang out with some number. In the other graph, vice versa. Whatever, y might be changing, but x is like, I don't care. I'm just going to do whatever I am. They're not related to each other. Right? Or a really common relationship could be like a linear relationship. Right? And these, a lot of times in this class, like go through the origin. Right? Not always, but oftentimes those would be linear. These first two are no relationship for, between y and x for particular. This could be a linear or direct, sometimes called direct. Okay. There was y versus x. Right. You guys remember, what's this called? Inverse. So as one variable gets big, the other gets small. As one gets small, the other gets big. Right? They're doing the opposite of each other. Right? We might see one of those later today. Right? There's, maybe like some kind of power relationship. Like this could be, I'll say power, but it might be like y equals x squared or something like that, some version of that. Maybe y x to a third. Right? And then what we're looking at right here is something more like this, some part of a root curve, okay, which is also a power relationship. It's just a fraction power, like y to the 1. If I have a y equals, I'm just giving you guys an example, x to the 1/2, isn't that the same thing as x squared of x, right? Could look something like that. Now, oftentimes with these graphs, and this has happened before, is that if you end up with a bunch of points up here, it might initially look like a straight line, but then if you extrapolate backwards, there would be a huge y-intercept. That's exactly what we're looking at in our example, aren't we? So that's all strong hints that it might actually be part of a root relationship, which it is. Okay. So where are we going with this? We're going with this is that we're going to linearize this, and this is a trick that AP really likes a lot. Okay. So I've shown you guys this before, so I'm going to very quickly recap this concept. Okay. What if you had let's say some form of a root, right? Y is, I'll say, proportional to the square root of x, for example, right? On a y-x axis system. Right? Maybe it's not the full equation, but it could be part of it. Right? Maybe y equals 3x times the square root of x, something like that. Right? If I suspected a square root, then what I could do is I could square both sides of this equation. Watch this. If y is proportional to the square root of x, this proportional sign, think like equals, but maybe I'm leaving out part of it. Right? What if I square both sides? Wouldn't it be y squared is proportional to just plain x? This and this say the same thing, don't they? Right? Funny thing I can do is I can manipulate the axes. Now, one thing you could do, you could go y versus the square root of x, or you could go y squared versus x. And either way, if it truly was a square root relationship, then shouldn't everything line up in a straight line like that? Right? And there could be some constant slope, right? Something like that. Right? Okay. And then, so let's try that out. Let me flip back over to computer present screen to share. Okay. And like this. If I square back, if I square the velocity, that speed axis, when I get v squared versus f, if I follow exactly what I just did, v squared versus f, and that should line up in a straight line. Let's see if it does. Oh, look at that. It's a straight line. Line of best fit, action line, geometric line. Add an equation if I want. Equation, right? Look at that. All right, so here's what we're going to do. Since we only got a few minutes of class left, we're going to just follow me here and just do what I do. Okay. You guys see this one that says v squared versus weight hanging? Label this axis v squared. Label this one, this horizontal axis f for the force. Okay? And just go ahead and dash a straight line goes zip like that. Okay? I mean, I've had you guys plot one graph. You guys have made lots of graphs before. The rest of these, we're just going to do that just to make sure we fit this in before the bell. Okay? Okay, great. So we have a linear relationship between the square of the speed and the hanging weight. You see that? That's exactly what the data shows. Let's see for the video. Let me make this bigger really fast. Okay, guess what I did? V squared versus f. It's a straight line relationship. Right? Okay, so back over to computer, present screen to share. Okay. All right. Okay, so we nailed down one of those relationships. Okay? And ultimately, everything is going to relate to speed squared. It's just how this plays out. It's the easiest way to do this lab. Okay. So let's nail down the next relationship. Let's go v versus the mass. Now this was the second experiment that we did. So I'm going to use that second data table. Okay. The masses that we used were mass. Yeah. Oh yeah. Here we go. Okay. It was 6 grams, 16, 26, come on here, 26, 31, 36, and 46 grams, right? Those are the mass values. Okay. Now, what were the corresponding speeds? They went 8.98 meters per second, 5.83 meters per second, 4.71, 3.99, 3.67, and 3.29. Did I plug all those numbers in right? Except, oh, that is a really pretty looking graph. Look at that. What kind of relationship is that? That is an inverse relationship, isn't it? Yeah, that's a really good job on did not start top on stopwatch. Wow, that is a really pretty looking graph right there. Okay, so how can I manipulate the axes to linearize this? Ooh, do you think maybe I should take the reciprocal of one of those variables? Okay. And I could do either one, but since I'm going to relate everything to v squared ultimately, let me go ahead and invert the mass, do 1 over mass. Is that true? Okay. So here's what I'm saying. Right, so that graph right there, do you guys see the bottom left graph on the front that says V versus mass swinging? I need to do a lot of switching back and forth here. Okay. So label this V versus mass, because that's exactly what the title says, V versus mass. It's always like Y versus X. Okay. And just go ahead and dash this line through. Just do that. Okay. If you want to do line best fit for the one you actually applied the points on, then it'd be like a square root looking kind of curve, right? Okay. This one's inverse, or reciprocal. So the next thing we're gonna do, you guys see this one to the right of it says V versus 1 over M. Okay, that's gonna be our next step. Now, this may or may not straight out into a straight line. We're gonna find out. Well, actually, I know this. I've done this lab before. Let's see. So I've got Excel set up. It's pre-programmed to take those numbers and take the reciprocal. Well, you guys can see that right down here, right? Let's see what those. Oh, look at that graph. Now, they don't line up in a straight line, but this looks familiar. This looks like a what kind of shape? It does look like a square root, right? Maybe it's a square root, maybe it's a cube root or a fourth root, but it does look like some kind of root. So again, just so we can fit this in for the bell, this is not good practice, but it'll get at the point of this lab. I want you guys to draw this relationship. Go ahead and just whip some kind of root curve going there. Okay? But now that we're at that point, well, we've been on this adventure before. We said, well, what we could do is square the speed, leave the horizontal axis what it is, which in this case is 1 over m. Okay? So we're taking this original set of data. We've already put it through one manipulation. We've manipulated the horizontal axis. Now we're going to put it through a second manipulation, and that's going to give us this middle graph on the right side. See where it says v squared versus 1 over the mass? Right? So it's v squared versus 1 over the, and you guys know that mass specifically refers to the swinging mass, right? So on this page, whenever you see the word mass, that implies a swinging canister. Okay? I wonder what this graph is going to look like. You guys got a guess? Yeah, you think it's probably going to linearize? Right? Let's see if it does. And I got Excel pre-programmed to do that ahead of time. Here. Oh, look at that. Look at that. Don't those dots line up into a nice straight line? Oh, got a trim line and everything going. Play the equation, why not? Okay. Yeah, so go ahead and just whip out a straight line on that one. Okay. Stop sharing. We're here. And so here's our basic relationship. Something like that. Of course, there are actual points it goes through, but basic idea. Okay, good so far? Okay, there's one more relationship we got to tackle, which was actually the first experiment we did. Remember the first experiment? I left the canisters alone, but I was changing out the radial size. Okay, that refers to this one right here. And okay, well, you guys see the pattern is that we're going to do some kind of axis manipulation, finish this graph, and that's going to lead to the answer. You guys see, we're on the home stretch here, right? Okay, so this graph comes from this particular table because that's the first data set we got. So let me flip my screen over. Let's see, present, screen, to, share. Okay. Yeah. These graphs are looking really nice. Okay. And then, oh, whoops, don't have that yet. Okay. So V versus R. So the radial values went, so 0.30 meters, 0.40 meters. And then from there, I just changed it 10 centimeters at a time. So let me go ahead and all the way down. Go one other place value. Okay. And then what the speeds we calculated, we got 6.93, 8.91. These would be in meters per second. Okay. We got a 8.61, 9.42, 11.13, 11.40, and 10.98. Right? What relationship do you think that is? That also looks like square root, doesn't it? Kind of, I mean, we only have like 7 points here. See, same thing, if you're playing around with different possibilities, let's say you thought this was linear possibly. If you assume linear, couldn't you extrapolate backwards and there'd be a huge intercept right here? Now let's think about what that would mean if that were the case. That would mean that at 0 radius, there would have to be like some definite speed that it was approaching. That didn't really seem to make a whole lot of sense, right? So it's probably not the case. It seems a lot more sensible that it would be a square root relationship. And scientifically, how to approach that is you could go back and get more data points from very small radial values that should kind of close in on this intercept, okay? But, okay, so go ahead and copy that. Just do what we've been doing all along. Just go ahead and label the axes V versus R, all else constant, okay? And draw a square root looking relationship there. Okay, so go fast. Yeah. You'll be able to put this in a time, right? So you guys got that, right? You guys got this so far? Okay. And you guys see where this is all going? This very last graph says V squared versus R, because we're going to do this tricky axis manipulation. Okay. We're doing pretty much exactly this again, right? So if you have some kind of root relationship, okay, if you square both sides, look like this, and if you were correct about the assumption specifically square root, then on a y squared versus x set of axes, it should line up into a straight line. Right? Let's see if that works. So I'm going to present screen to share. Okay. So I've got Excel pre-programmed, just like with the other one. Okay. It's, where's my, okay. To get V squared versus, oh wait, where's my graph? Oh, there it is. Right? Hey, look at that. Now that's a nice line that goes, okay, actually does kind of miss the origin, but yeah, not too bad. Right? Ideally, there's a straight line. Right? So that's where this is going. Right, so go ahead and make drawing that last graph right there. Right? And that's just a linear relationship. Right? Yeah. It's interesting that, yeah, this one, I missed the intercept there, but that's all right. Right. So you guys got all that? Okay. Yeah, so stop sharing my screen, flip over, projection. Okay. Now let's go in for the formula. Okay. So what do we figure out? You guys see the first box, it says, how are these 4 variables related? The hanging weight, the swinging mass, the speed, the radial size. Okay. And everything, oh, look at these 3 graphs above it. Aren't they all related to V squared? So I've got V squared is proportional to, isn't it directly proportional to the force, which is the hanging weight, of course, which is representing the centripetal force? Isn't it, go down to this very bottom graph, isn't V squared directly proportional to the radial size? So F times R. And isn't it also proportional to 1 over the mass? So divide by a mass. So you see I have F times R divided by M, right? Now, the box to the right says just rearrange that and solve for F. So once you cross multiply up the M, divide down the R, and we get force is proportional to mv squared over R. That is the formula for centripetal force. We proved that empirically, right? Actually, one last little tidbit. This is proportional, but with that, since you guys know this really would work as an equal sign, what would happen if you multiply this slope times this slope times this slope? What do you get? If you multiply all the slopes together, you get 1, because this would be an exact equation, not just a proportionality. Okay, you guys get that? All right. So, like I said, we're gonna break convention here. I'm not actually gonna have you guys do a write-up for this. As long as you guys have at least the data that I've written. If you haven't filled in those other columns, that's okay. You guys get where I was going with that. have the data, have the graphs, have at least that one plotted and the other one's just this line put out, and have these equations. Pop that in the grade tray, or if you're online, then upload that to Focus, and it should be easy class for this one. Who's got big questions? Yeah, so John's really good with the stopwatch because those graphs look really nice.
I am done.